Hello friends, strangers, and everyone in between. Today we're going to be talking about using the CAN API on Olin Electric Motorsports. So we're going to go over a quick overview, talk very briefly about how the API works on the back end, and then go through a coding example of how we actually use this. So to begin, our CAN library is designed to automatically generate C code that abstracts CAN bus interaction for our STM32 G4 microcontrollers. The reason our team has this library is that some of the kind of nitty-gritty peripheral code for interacting with the CAN bus is repeated across many files. So we have chosen to streamline it by kind of moving it to one place. And this system also allows us to kind of develop a unified way to send and receive messages using a DBC file and edited with YAML files, which are very easy to write and read for humans. And all the content on this is kind of designed around the current version of the library as of April 2026 and the Mark 8 firmware. So how does the CAN API work? I'm going to switch over to this digital whiteboard here and we'll take a look. So it might look like there's a lot going on, and to some extent there is, but once you kind of understand it, it's not too bad. The main things to note here are we have a YAML file within the kind of individual board implementation. And this YAML file kind of defines the messages that a board will send and receive. Using that YAML file, our library, which is located over here, will generate those C code files and the DBC based off these templates. We won't go too far into how that works on the back end. We might cover that in a future video, but all you need to know is that there are these API files that are generated at compile time when the code is compiled that contain all these useful functions that we'll get into. All right, moving on to the first step in using the CAN API, which will be YAML setup. There are 3 steps for using our CAN API. The first is the YAML file setup. So we're going to hop into a code editor here, where we have some example files for us to look through. So hopefully this file structure looks somewhat familiar. Your project will be housed something like this. There will be a folder that contains a build file, likely a name_config.c, name.c, name.h, and then you'll either have to add or modify the name.yaml file. So the name of this node, or node, MCU, project, different things we could call it. I'm going to refer to it as a node in this video, but the name of this node is test_rx, and that's where we're going to start. So we're going to open up the YAML file here. If you don't have this, you would create it, and we're going to take a look at what we see. This one's pretty simple, but looking at the first line, here we have the name. This should be the name of the node. Again, in this case, that's test_rx. And then we go into subscribe. This indicates what messages that this node should receive from CAN. In this case, we just have placed once, and the name of that message is message1. To receive a message, this is all you need to include in the YAML file. Of course, you can receive multiple messages, just add more entries to this list. You'll also notice we have publish here. There's nothing under it. This node will not be publishing or sending any messages to the CAN network. Now we're going to move on to a different node, which we're calling test TX, test transmit. And we're going to take a look at the YAML file there. Right away, you'll see it's a little more complicated, but same structure. So we have the name of the node, which in this case is test TX. The subscriptions, in this case none. This node does not receive any messages. It only sends messages. To be clear, nodes can absolutely send and receive messages, but for the sake of this example, we've chosen nodes that only do one or the other. So diving into this publish list, this is where we list all the messages this node will send. Again, a node can send multiple messages. As shown here, we have 2 message examples. And we're going to take a look at what goes into each of these messages. The first thing is the message name. First one, we're calling it message 1. This should be kind of a unique name within the node, within the published messages. And it hopefully should be descriptive to what you're sending. Next, we have the ID. And actually, one more note on that name here. You'll notice that message 1 is the name of a message is how you refer to it, for example, when receiving it. So if we pop quickly back to that test RX YAML, you'll see that message 1 is the same as the name of this message here. So this node would receive this message. But moving on to the ID, each message in the entire CAN bus must have a unique ID. The number of the ID does matter. The lower the ID number, the higher priority it is on the CAN bus. And if you're interested as to why, you should look into the CAN hardware videos we have on the OEM YouTube channel. It's pretty interesting. So unique ID here. And then next we'll go into the frequency. This determines how often the message is sent, and it's measured in hertz. So a value of 100 indicates the message will be sent 100 times every second. Generally speaking, there isn't a strict upper cap on the frequency, but do keep in mind the more often you send a message, the more it will start to crowd out the CAN bus. On our bus, once you approach roughly 2,000 hertz, that message will represent 50% of all traffic possible on the bus, which could start to be problematic depending on what else is happening. So generally, 100 is a reasonable range for a message, reasonable range for frequency that a message should be sent. Yeah, depending on your specific application, that might be higher or lower. So each message is divided into signals. And for each signal, there's a couple of things we need to set. The first is the name of each signal. We've called this one dummy signal. And the second is the slice here. The slice determines, or each CAN message has a data field of 64 bits or 8 bytes. That's defined by the classic CAN standard that we use. And it's up to us to determine how we fill that data field with our signals. And the format for this is we have the start bit, in this case 0, and the length of the message that we'll be sending. So you'll notice that this is a 64-bit, sorry, not the length of a message, the length of a signal we'll be sending. You'll notice this is a 64-bit length here, which indicates it's going to take up all 64 bits in that data field. When we look at message 2, we'll look at an example of why this field might be useful, but for now we'll move on to unit. Each signal has a unit. That determines the type as well as some other information, depending on the type. So in this case, we have an integer unit, specifically a 64-bit integer unit. And when we're using an integer unit, or integer type, I should say, we also have to provide a name, offset, and scale. For now, you might not have to worry too much about what these fields actually mean. This is primarily used in our DBC database and tools such as CAN Viewer for putting context around that value. But one message can have more than one signal, and we'll take a look at message 2 to see an example of that. So this message 2 has 3 signals within it, and we'll take a brief look at what that looks like. You'll see this first one here. It's a Boolean representing the system A status. Since it's a Boolean, it only takes up 1 bit. Likewise, for the second signal here, it's a Boolean and it only takes up 1 bit. That's the length. But notice how instead of starting at 0, we're now starting at bit 1, since that first kind of space is taken up by the first signal. And the first 2 spaces are taken up by the time we get to signal 3, which is why this slice starts at 2. And this is a slightly longer signal at 8 bits. And this signal has the type of enum. In this case, enum, we have to specify the values for that enum. And this is important because you can think of it as providing kind of important context to what that enum actually represents. And this will, I suppose, match the code written wherever this is being defined / edited. So yeah, keep that in mind. One more brief note on the slices. You'll notice you might be wondering why we have to bother with this at all. The reason for this is, as we mentioned earlier, the maximum kind of data size is 64 bits, so it's somewhat limited. So we sometimes do what's called bit packing in order to maximize this. So typically, when you're storing data, it often is aligned by bytes in kind of increments of 8. So if you had 3 signals like this, and maybe a typical storage scheme, it would take up 3 bytes of data, which is a lot of space that we might not have available to us in this data field. So by kind of specifying individually where each bit will end up in the kind of data payload, we can essentially pack down these smaller signals into smaller bytes. So instead of taking up 3 bytes, which would be 24 bits, this whole sequence of signals only goes up to bit 10. All right, moving on to the Bazel integration step. Once we have our YAML file created, we have to do a couple small things within Bazel in order to integrate it with the rest of the car and our kind of repository build system. So the first thing we're going to do is either create or modify build files for each of our nodes. So starting with test.rx, we're going to open up this build file and take a look at what we have. You'll notice a couple things. The first thing to point out is this line, the second line right here, which loads in the CAN API rule. This is required for us to actually use the CAN API. And we kind of create this kind of Bazel command here, which specifies the options for the CAN API. We give it a name, we point it to the YAML file, as well as the DBC target. You'll notice in this case, it points to the example DBC. Likely in your code, this will point to something like vehicle /mark8:mark8. Another thing to notice is we have to add this exports file command. This indicates to Bazel that this YAML file should be viewable from elsewhere in the system, and that is required for the CAN API. And the final thing to note here is that we also include this dependency on the CAN API within this command. The rest of the content of this command relates to the kind of programming and flashing aspect of the firmware and isn't exactly relevant to this video, but it's important that we include this dependency for everything to function correctly. And the final note about Bazel is that there's one more place we need to make a change, and that's within the kind of base level repository, or base level build file. So in this case, that's located under vehicle/examples, but likely for your code, that'll be located under vehicle/mark8. But if we take a look at this Bazel file, you'll notice this dbc gen. This is the dbc generator command, and we need to provide the, reference or links here. So you'll notice we added these two lines to the end, which contain the path to the node. So to test RX and to test TX, and then colon, and then the name of that YAML file. And with that done, the Bazel setup is complete. All right, with the YAML file complete and the Bazel integration step done, we'll now move on to implementing the CAN API within your firmware. So we're going to switch back to the code here. And we're going to look at the test RX node first. So let's open up that C file. And a couple things we want to notice here. The first thing to notice is this include statement right here. We want to be sure to include the CAN API header file so that we have access to everything. So that's step one. Step two is we need to actually run the initialization command for each node that we want to be using the CAN API. That can be seen in here. Notice that this is being run sort of in the setup phase before that main loop, but within the main function. So this command right here, can init underscore, and then the name of the node here. So at first, it might be a little confusing when using this, as we never defined this function explicitly, and that's kind of unusual for what you might be used to writing code. But rest assured, the API will define this function at compile time. So even if you can't see it now, it will be there when it's time to actually run. So keep that in mind. The general pattern for using this API is that things are generated at compile time. So yeah, running this command is what actually kind of initializes the API and prepares us to send or receive messages. You'll notice that this is wrapped in a if block, which might be a little confusing to look at first, but essentially what we're saying is that this function we know returns 0 if it's successful, and it returns something else otherwise. So what this if block is doing is we're checking whether it's successful, and if it was not successful, we enter the if block and we do something. In this case, we're holding the CPU with a infinite while block, but depending on your use case, this could do something else. This if block isn't explicitly necessary, but in some situations you want to catch whether the initialization failed to prevent perhaps strange issues down the line. All right, so now we have everything initialized. Let's move on to receiving messages. So if you look a little further down within the main loop, you'll see this can underscore poll underscore receive all. This is the function that we use to receive messages. Like the initialization function, it's defined elsewhere, but it will exist. When you call this message, it will check whether there's new received messages, and if there are, it will update a designated struct for each message. So again, I'll emphasize this is a little bit strange to think about, but just understand there is a struct being created for each message that the node will transmit or receive. And as a reminder, for this node, if we take a peek at the YAML file, we see that there's exactly one message that this node will receive. And the name of that message is message1. So seeing that, we know that the CAN API will automatically create a struct with the same name called message1. And then on the next line here, you'll see that we actually read the value of a field from that struct. So the name of the struct is message1, defined by our YAML. And then we access the signals from that message with the dot notation, followed by the name of the signal. So in this case, we're accessing the message called message1 and the signal called dummy signal. And we're assigning that value to some arbitrary variable in this example. So you might be wondering, how do you know the name of the signal? Again, recall that in the whenever we transmit the message, we have to define exactly that. So if we find where that message was sent from, in this case that would be testtx.yaml, we can pull up that YAML file and take a look. Again, notice message1 here, the name of the message, and notice that this message has one signal named dummy signal. If we were looking at message2, the struct would be populated with message2.systemA message2.systemB status, message2.faultcode, and any other signals if they existed. So that's how we receive messages. How do we send messages? So we're going to take a look at test_transmit.c for an example of that. First thing to note is that we have some of the same patterns that we saw in our test_rx node. We still have that include statement. We still have the initialization statement. That all looks the same. What's different here is that within the main loop, instead of calling the receive function, we're calling a send function. But before we do that, we need to actually update the information to be sent. So much like how we receive messages, we do this through a struct with the name of the message. So again, we're still talking about message1 here. So we have the name of the struct, message1, the name of the signal, dummy signal, and we're assigning that field with the struct to be my variable, which again is an arbitrary variable we defined up here. Notice that the type of this variable matches the type defined by the signal here. In this case, it's a 64-bit integer. So we've updated the message struct with a new value. And now we can move on to actually sending it. So the send function is pretty straightforward. We say can send underscore, and then again, the name of the message. In this case, that's message1, and that will automatically send the message to the CAN bus. One quick thing to note here is that you can wrap this can send as well as the can pull receive all functions in that same sort of if block that we have up here. If you want to do some more advanced error handling, that might not always be necessary or useful. Oftentimes, if we miss just one message, either sent or received, it might not be critical. But depending on your application, that's something to keep in mind as an option. All right, so now you've learned how to define your YAML files, integrate with Bazel, and implement all this within your firmware. You should be all set to go, and I hope you enjoy using the CAN API. A couple of resources to keep in mind when working with this API. The README within the OEM monorepo is very helpful. Has all of the kind of instructions talked about in this video documented in a easy to reference form. That content is also mirrored on the Coda reference page, as well as the Mark 8 CAN address space is the spreadsheet I mentioned for determining the ID of your messages. That's all for now. Thanks.